This is the video in section 12.5, areas and volumes of similar solids. We learned about similar triangles a while ago. We call it the word similar means the same shape, but not necessarily the same size. When two things are similar, their angles are congruent, and their sides are in the same proportion. So we're going to extend that now to three-dimensional figures. Two three-dimensional solids are similar when the bases are similar to each other, and when the corresponding lengths throughout the solids are proportional to each other. So are these two orange cylinders here similar? Well, their bases are both circles. Circles are always similar to each other. And if we look at the proportion of the radii, 6 on the big one to 4 on the small one, that reduces down, if we divide by 2, to 3 over 2. And if we compare that to the proportion of the heights, 12 over 8, that reduces down, if we divide by 4, to 3 over 2. So they're in the same proportion. So yes, these are similar to each other. How about these two green pyramids here? Their bases are both squares. Their bases are similar to each other then. The heights are a ratio of 8 to 4, which reduces to 2 over 1. The slant heights are 10 to 5, which also reduces to 2 over 1. And then the side length of the base is 12 to 6, which also reduces to 2 over 1. So yes, they are similar with a scale factor of 2 to 1. The scale factor on the first example here of the cylinders was 3 to 2. So when things are similar, we know the ratio of one to the other. And this theorem allows us to apply that then to the perimeters, the areas, and the volumes of those solids. If the scale factor of two similar solids is A to B, then the ratio of corresponding perimeters is also A to B. The ratio of the base areas, of the lateral areas, and of the total areas is A squared to B squared. And the ratio of the volumes is A cubed to B cubed. So let's see how that works. The prisms here are similar to each other. Find the ratio of the base perimeters, the ratio of the lateral areas, and the ratio of the total volumes. So we're given only one side of each of the bases, so we could not directly find the base perimeters, we could not directly find the lateral areas or the volumes, but we're only asked for the ratio of one to the other. The scale factor, and we'll just go from left to right here, is 6 to 10, which reduces down, if we divide by 2, to 3 to 5. We can express the scale factor as a fraction or as a ratio, 3:5, either way is fine. So the base perimeters, which would be the perimeter of the triangle that's at the base of each of these, the base perimeters have a ratio then that's equal to the scale factor, 3 to 5. The lateral areas, if you look at the theorem, have a ratio equivalent to 3 squared to 5 squared, which would be 9 to 25. And the volumes have a ratio equivalent to 3 cubed to 5 cubed, which would be 27 to 125. Simple enough. If it's area, square both of the numbers in the scale factor. If it's volume, cube both of the numbers in the scale factor. Two similar cones have bases with areas in the ratio of 9 to 4. Find the ratios of the radii, the heights, the total areas, the circumference of the bases, and the volumes. So we are given the ratio of the areas, which means the scale factor is not 9 to 4, because the areas are squaring the scale factor, so the scale factor must be 3 to 2. The radii are just lengths. They're not areas, they're not volumes, so they're also 3 to 2. The heights are also lengths. They're not areas or volumes, so they're 3 to 2. The total areas of the cones are areas, so we square the scale factor. That's 9 to 4. The circumference of the bases, circumference is a measure of perimeter, of length, so it's just 3 to 2. The volumes we have to cube, so it's 3 cubed, which is 27, to 2 cubed, which is 8. A regular pyramid has a height 18 and a total area of 648. A similar pyramid has a height of 6. Find the total area of the smaller pyramid. So we know they are similar to each other. It tells us that. We know the heights of each one, 18 and 6. So 18 to 6 has to be the scale factor. That reduces down to 3 over 1. Okay, we're interested in the areas. So the ratio of the areas is going to be 3 squared to 1 squared. 3 squared is 9, 1 squared is still 1. So the ratio of the areas is 9 to 1. So we'll set up a proportion to be able to go from one area to the other. 648 was the bigger one, so it corresponds with 9, which goes with the bigger pyramid. And we'll call the one we don't know, the area of the smaller pyramid, x. And we remember we solve proportions by cross multiplying. 9 times x equals 648 times 1, which is 648. And then 648 divided by 9 is 72. So 72 is the area of the smaller pyramid. So if you have the scale factor, square it to get to the ratio of the areas, and then use the proportion to go from one of the areas to the other. If you were doing a problem on volume, you would cube the scale factor and then set up your proportion with that ratio. So here are your immediate practice problems. A cylinder has a radius of 7. A similar cylinder has a radius of 14. Find the ratio of their lateral areas and the ratio of their volumes. And number 2, for the same cylinders, if the total area of the smaller one is 168 pi, find the total area of the larger one. Use the format that we used on this last example. That's the end of section 12.5.